In the last video we have made regarding the harmonics. We have explained what are harmonics and how they are created. In that harmonics video or topic, we have introduced one thing that is known as the clipping, and I told you two rules for that. That one is that symmetric clipping, it's always produces the odd harmonics, and asymmetric clipping, it's always produces the both even as well as the odd. But in this video we'll be discussing what's the reason for that, right? And more importantly, that when you see these even harmonics in a spectrum, so can you connect to that specific fault on a real machine or not, right? So that's why that's what this video will be about. So we'll be discussing first concept, and then we will be also taking few examples from the field. Okay, so first one, let's start with the symmetric clipping. So symmetric clipping means the waveform hits a physical limit equally on both sides. Okay, the positive peak is flattened by the same amount as the negative peak. So imagine a sine waveform, okay, with two horizontal lines drawn at equal distance, one above and another one is below the center line. Okay, anywhere the waveform crosses between those two lines, what happen, it will get cut, it will become flat. Okay, so the both peaks are equal. So now here is the key question, that why does this produce only odd harmonics, right? So the real explanation basically comes from the concept of FFT, or you can say this is how the FFT or fast Fourier transform actually works. So what happened here, that FFT detects a harmonics frequency by doing one specific thing. What is that specific thing? That it multiply the signal by that harmonic frequency. Okay, and then what happened, that it will measure the total area under that result. Okay, so if the area above and the below of the center line cancel each other perfectly, that means there will be no harmonic. Okay, there will be no harmonic exists, because the net area is 0. And if there is some portion of net area remains, or any difference is there in the area above the center line and below the center line, that means the harmonic will be present in the spectrum. Okay, so just think about a weighing scale. Okay, if the result balances equally, so that means you will not see any harmonic, or you can say the harmonic is absent. Or let's say that if one side is outweigh, so there definitely there will be the harmonic. Okay, so now let's test the second harmonic, or 2x on a symmetric waveform. Okay, let's understand that how this 2x comes. So the 2x harmonic completes exactly one full cycle in each half of the fundamental. Okay, or you can say the two full cycles in one complete revolution of a machine. Okay, so now what will happen, that multiply this symmetric clipped wave, the original signal, the wave, by the second harmonic. Okay, so what will happen here, in the first half the product creates some positive area, and definitely some negative area will be there. Okay, now again look to the second half of this signal. Okay, what you will see here, because the waveform is exactly perfectly mirror, okay, flip of the first half. So what happens, that the exact same area will appear again. Okay, but the order will be reverse now. Okay, so the positive form of the first half, what happened, that it will cancel the negative of the second half, and vice versa, right? So overall the net area will be 0. So okay, so the second harmonic simply does not exist. Okay, this is not like any kind of a coincidence, or any kind of it's just a mathematical calculation of a symmetric waveform. Okay, so this is the reason that why we don't see the even harmonics in a symmetric waveform, and the same logic will be applying for the 4x, 6x, 8x, right? So now we will be discussing that what is happening in the waveform, if let's say that with the 3x, or you can say the third harmonic. Okay, so now imagine that the three complete revolution in complete one cycle. Okay, that means the half cycle consists of the 1.5 cycle of this harmonic. Understand? Okay, so that half cycle offset means the second half does not produce the exact reverse of the first half. Okay, the pattern is different, because this time there is a 3 cycle, like first it will go up, then it will go down, then again it will go up, right? Then again from the next session, or you can say the second half signal, what will happen, it will reverse, right? It will not exactly mirror. What will happen, it will reverse. So when you multiply and measure the area, what will happen now, if you just see the picture, and if you just imagine, and you know, if you will start measuring the area, what will happen, you will see that the positive side is, you know, consistently what is, it's outweighs the negative side. Okay, so the net area, always there will be some net area, always something will be remaining, right? So the third harmonic is always detected in this case, right? So the same thing will be happen with the 5x, 7x, 9x and all kind of odd harmonics. Clear? Okay, because it's not the mirror, it's exactly the repeating the things, right? So now let's say that if I will take the example of this, so what will be the result in the spectrum? So normally in the spectrum you will be seeing first of all 1x, and then directly you will be seeing 3x, 5x, 7x, or you know, all kind of odd harmonics. There will be no at all the even harmonics in this case. Okay, so in the field, if you want to take the example, just imagine, just take the example of, you know, some kind of a rocking movement of a shaft or a bearing between two hard stops. Okay, so here you will see that the shaft will go up, hit again, then come down, then hit again. They're kind of a rocking movement, both sides the restrictions are there. So in this case you will be always seeing the 1x, then 3x, 5x. So whenever in the spectrum you will see the odd harmonics and that are very dominant, that means there is definitely, once you open the time waveform, you will be seeing a symmetric behavior. Okay, what you will see, you will be seeing a symmetric behavior. Okay, so now let's move to the next one, that is the asymmetric clipping. Okay, so now what happened in the asymmetric clipping? So here one thing will be changing. What? The machine will hit only in the one side. Okay, so let's say the positive peak, they get clipped, and the negative peak is free. Let's say, imagine like in this way. Okay, so we'll be taking the examples based on that. So definitely the two halves of the waveform are now completely different, because one side it's hitting to some part and another side is free. Okay, so one side is flat topped and the other side is full smooth curve. Now we will be applying the same test that we did before. So and we will be multiplied by the second harmonic, and we will be measuring the area. So the same concept we are going to do that we did with the symmetric clipping. So in the first half, what happened, the clipped half, the product generates a certain pattern of the positive and the negative area, right? And in the second half, there will be a free, or you can say one will be the free, and there will be an unclipped half, right? So the product generates a different pattern, because one pattern, the first pattern is the clipped one of the main signal, right? And the second pattern is a free one. So definitely the portion or the waveform that will be in the clipped one, that will be different, right? The area will be different, and of course the area with the free one, it's different. So there will be a mismatch of the area, or you can say the both the areas are not equal, or you can say the waveform shape is different. Okay, so the areas from the first half and the second half are no longer equal and opposite, right? So now what happened now here, so that means they will not cancel each other, right? That's the reason that 2x harmonics will be detected now in this case. Why? Because their area is not cancelling and becoming zero here. Okay, so that's the reason, this is the fundamental reason, you know, even that the even harmonics will be appearing in the asymmetric clipping, and the mirror cancellation that destroyed a 2x, remember in the symmetric case, that no longer works here. Okay, because there is no mirror, right? Because the area is fully different. Okay, so the stronger that we will be getting the asymmetric signal, what will happen, there will be the more different two halves. That means the more difference in the area will be there, so there will be like a more stronger even harmonics in that case. Okay, if there will be mild symmetry, what will happen, there will be a slight difference in the two halves, so you will be getting a even harmonic, but the amplitude will be small, or you can say the amplitude will be weak. Okay, and in the another case, let's say if there's a severe asymmetric case, in what will happen, that one side will be heavily clipped and other side is fully free. So what will happen, it will give you a strong even harmonics. Okay, sometimes, you know, it will you know, it can be more than even than the fundamental or you can say the 1x. Okay, so the odd harmonics, but here the odd harmonics are still there. Why? Because distortions always generate them regardless of the asymmetry. If you will just refer the just move this video back and just refer the concept that we discussed for the odd harmonics in the symmetric portion. Okay, so because of the distortion, it will be there, right? So what will the result here in this case, in this spectrum, you will be seeing the full series, let's say 1x, 2x, 3x, 4x, 5x, 6x. Okay, so That means the even harmonics are not any kind of a random noise or something like this. Okay, they are the direct signature of an asymmetric condition. Something that means something happening to one side of the machine, or you can say the one side of the machine's motion compared to the other, right? So this is how the same thing that you can open in the time waveform, and you will see the difference that one side the one either the top portion of the waveform or the bottom portion of the waveform movements are different. Okay, and if there will be such kind of case, what you will see a complete 1x 2x 3x 4x like this. Okay, so overall the let's make it one kind of a confirmation step, and we will be just discussing that what we have discussed till now regarding the symmetric and asymmetric. Let's draw one center line through the time waveform, and if both the peaks are flat, let's say the equal height above and below, what you will be seeing the symmetric. So open and go and look for the odd harmonics, it will always be present. Okay, and in the case where one side is flat and the other side is smooth, or you can say the round, so that means it's a symmetric pattern. Go and definitely look for the even harmonics. Even harmonics definitely will be there along with the odd. Okay, so let's say that if my waveform is off center, in this case also the same, that it's also a symmetric pattern. In that case you will be seeing a dominant 2x, or you can say the dominant even harmonics. Okay, so always you should remember that whatever you are seeing the spectrum or whatever seeing in the waveform, it should always agree with each other. Otherwise maybe the diagnosis can be wrong, or you have to little bit do more diagnosis on that particular machine. Okay, so these are the things I think you will be enjoying when you're doing the practical. Definitely you will enjoy this thing, and just observe this thing whatever I explained you. Next time when you are collecting the data, or you already have some kind of a collected data, just try to identify the symmetric and asymmetric time waveform and try to compare it with the spectrum. Okay, and let's not assume, I'm sorry for that. Let's take some examples now. Okay, some practical examples. So let's take first example of let's assume that mechanical looseness, some kind of mechanical looseness is there. So mechanical looseness means it will be forming a symmetric clipping type of, right? Because what happened, let's assume that the bearing is loose in the housing. Okay, so in that case what will happen, the rotating component, what will happen, it will swing freely until it hits the clearance limit. Okay, so what is the clearance limit? Let's say above. It will hit above, then it will come down and swing it back and hit the lower limit. So one, it will be swinging and hitting again the upper limit, then again swimming back and hitting the lower limit. That means equal contact and the equal constant. That means in that case in the both sides. So what will happen, the both sides the areas are same, areas are same, then definitely 2x we will not able to see the even harmonics, so 2x will be cancelled. So in this case what we will be seeing, the odd harmonics, 1x 3x 5x 7x. So whenever you see in the spectrum the odd harmonics 1x 3x 5x 7x, so always you should remember one thing, that there can be there should be the restriction on in this for the shaft both sides, or for this bearing both sides. Okay, clear? In the same way, if you will take the another example of the crack shaft, that is an example of the asymmetric clipping. Why asymmetric clipping? Let's say there is a one crack in the shaft, okay, one side, so there will be two movements there. There will be a soft movement, one there will be a half movement. In, let's say my shaft is rotating one complete revolution, so when it come down under the load, it will be like crack will be slightly open, and when it's go without load or go upside, the crack will be slightly closed. So the crack will be open close open close. So in one cycle the you will be having the two movements here, right? Two movements, and the both movements are different. Okay, one side the movement is free, soft, you can say, and one side the movement is hard. Okay, so that is the restricted one. So what will happen now, it will create a asymmetric clipping, because one side is free, one side is soft, and one side is hard. So in that case, remember what you will see now, you will be seeing the even harmonics. Okay, you will be seeing the even harmonics because both sides the areas are different. One side the area of the clipping, one side the area of free one. So you will be seeing the 2x, okay, 2x 4x 6x, and also you will be seeing the odd harmonics also. Or in the simple way you can see, you will be seeing a series 1x 2x 3x 4x. And especially in the in the crack shaft issues, normally we will be seeing the dominant 2x. Okay, the dominant 2x, because as the crack will develop more, so you will be seeing that slowly the 2x will be more compared to the 1x. But here we will not discuss this thing. Here this we will be clearing the logic of symmetric and asymmetric clipping. Okay, so or you can say the odd and the even harmonics. So third example we can take of the rotor rubbing. In the rotor rubbing also it's a kind of asymmetric, because one side when the movement is there, so one side movement will be restricted. Let's say the rotor is touching one side of the bearing housing, or you can say one side of the any kind of a motor cover, and another side is free. So in this case what will happen, again the asymmetric clipping. So what you will see here, you will be again seeing the series of harmonics. You will be seeing 1x, 2x, 3x, 4x, and even you can see up to maybe more than 10x. Okay, so in the last, let's conclude this video. I hope you're very much clear about symmetric and asymmetric clipping. Okay, so symmetric clipping means odd harmonics only. Okay, symmetric clipping means odd harmonic only because both sides are equal, or you can say the both sides are clipped. Okay, so in that case what will happen, there kind of any kind of a mechanical looseness this or something is there, what will happen, that one side restricted, another side is also restricted. So both areas are similar. In once the both areas are similar, then I will not have any 2x, I will or you can say the even harmonics, I will be having only odd harmonics. And another example of asymmetric clipping, in this case what will happen, that the even and odd both harmonics will be there, because one side is restricted but another side is free. Okay, in this case the area will always mismatch, or you can say there will be always some kind of a difference will be there between the areas. So always you will see all kind of harmonics, 1x, 2x, 3x, 4x. Okay, and always we should make sure that you should be confirming the spectrum. Whatever you are getting the spectrum, always try to compare it with the time waveform. Please make sure that after having listening to this video, you should be going and compare this stuff, that whatever we discussed here. Okay, so you will be you can very easily identify the difference between the symmetric and asymmetric clipping, and based on that your analysis will be more perfect, and you can very easily say that what kind of movement or what kind of looseness is happening inside that particular machine. Okay, so we'll be meeting you in the next video, okay, with the next topic in this vibration series. Hit like and subscribe and drop a comment with any kind of a real case, or if you have any kind of new case or any kind of questions you have, please drop the comments. I will try to answer that. And till then, take care and take care of your family. We'll see you in the next video. Take care. Bye.